Let us now study a small algorithmic problem called stable matching that, to be modeled with constraint programming, extensively uses the element constraints. In this problem, you have a set of persons and a set of companies. So these are the persons, these are the companies. Both sets have the same size, so in this case we have 4 persons and we have 4 companies. And the goal in this problem is to decide in a hiring process who will go where, so which person will work for which company. And of course there will be only one person per company, so that's what we call a matching. And each person in this problem, each person expressed some preferences for each company. And each company also express some preferences over the person that they would like to have, to receive. And since we don't want to have a turnover of the persons, we would like the matching to be stable between the persons and the companies. So what does it mean for matching to be stable? Let's take a few examples to explain what we mean by stable, because that's not so simple. For instance, IBM has received some persons, right? Some person, and IBM would rather prefer to have George instead of, for instance, Ali. But George doesn't want to move, and so he would prefer to stay at IBM. So he has no incentive to move, and that's not the case of IBM, who would like to receive George instead. Let's take another example. Ali would prefer to work for NASA, but NASA prefers to stick with the person that it has received. And so we have also no clear incentive to change the matching in that case. This is what we mean by stable. And we would like to express these rules in terms of simple constraints in CP. And as we will see, that will use element constraints. So more precisely, in input, what we receive is this. So we receive a ranking of, for each company, of the ranking of the persons, and for each person, the ranking of the companies. And the problem is to do a matching between the persons and the students so that the stability rules are satisfied. So let's take one example. So I received 2 matrices there. Okay, I received here the rank of the students for each company, right? So for instance here, Google would prefer to have first George, then Ali, then Keira, then Clive, and IBM would rather have first Keira, then Clive, then Ali, and then George. Okay, and we have the same type of ranking for each person there, for each student. So each student expressed their ranking for the companies. For instance, George would prefer to work first for Google, then IBM, then NASA, then SAP. But Clive would prefer to work first for NASA, then SAP, then IBM, then Google. And that's one possible stable matching. You can convince yourself that all the stability rules are satisfied for this example. Is this problem a difficult problem to solve? No, it's not difficult. There is a polynomial time algorithm for solving that problem, and you can find the link on Wikipedia for solving that problem. But still, it's a good exercise to model it with CP. We now describe the CP model for the stable matching. Since we will implement this problem in a programming assignment, I don't give the mini CP code, and instead I will use a pseudocode of CP in a typical high-level modeling language called OPL. Let us start by describing the 2 input matrices of data that we receive for that problem. As you know, we will start the data that we will receive is the ranking there. You will have the ranking for each student considering the companies, and for each companies considering the students there. In terms of decision variables, what we have to decide is for each student there, which company it should choose. And so the domain of each student variable, there is one variable for each student, is the set of companies. And in the opposite direction, you have one variable for each company, and you need to decide for each of them which student it will receive. Okay, so that's the decision variables of our problems. the first constraint that we will enforce in our model are just consistency rule to make sure that the errors are reciprocal in the matching. So if the student S if the student S receives some company, then that company must also receive the same student. So if you want, it's to make sure that the errors from the students okay, so if you have a student S receiving the company C, then we also make sure that the company C receive exactly the same student in the other direction. What kind of constraint do we use to model this set of constraints? What you can see that what we need to do there is index an array of variables there, and we index it with the variable as well. So it's an element constraint, sure, but we index an array of variables by a variable. I'm not sure that's exactly the same type of element constraint that we have introduced just before. Okay, maybe we will need another generalization of the element constraint, and we will introduce it next. Let us now describe the stable matching rule for every student and every company. Okay, so remember in the ranking, the lower it is, the better it is. Okay, so we consider every pair of student and company. So if you see that these students, okay, would prefer to move to the company C instead of the company that it has received, that's not the case. That's not the case for the company itself, because the company C has ranked the student that it has received better than the student has. And we also need to enforce the same rule in the opposite direction. So we now consider every company, every student. If we realize that this company would prefer to receive the student S over the student that it has received, that's not the case for the student S. The student S would prefer to stay in the company that it is received instead of moving to the company C. And you can see that this is an implication constraint there. It's really a Boolean implication there, a logical implication. Okay, that's the complete model where you can see the input data there, and you can also see the decision variables, and then we have the set of constraints there. It's a feasibility problem. It's not an optimization problem. It's really a feasibility problem. The goal is to find a stable matching to that problem. What kind of constraints do we need there to model that problem? As you can see here, we have the non-standard element constraints because we are indexing an array of variables by a variable. Okay, so we will need to extend a little bit the definition and the genericity of the element constraint that we have seen so far, and in particular 1D element constraints. For the other set of constraints, first you see that we have this logical constraint, but we also need element constraint there, okay, and that's 1D element constraint because C is the parameter of the loop, so it's fixed to some value, and we index so that row of that particular ranking matrix, so it's a 1D array by a variable. So that's the standard element constraint that we have seen before. But we need to find something new here for that constraint, and this is what we will introduce in the next video. So we have seen very interesting features in this model of the stable matching problem. We have seen a lot of use of element constraint. We have seen logical combination of constraints. We have seen the ability to index an array of metrics with a variable over an expression containing variables as well. So that's new. That we need something to introduce something new in the next video again. And we have seen logical combination of constraints that were handled with reification, because here for this logical constraint, you see that we have a Boolean expression there. We need to test if this is the case, that this is less than this part there.